I'll be out of town next week. Unfortunately or fortunately, I have to go to Australia. And
oh, so tough.
It's unfortunately because I think I fly for 2 days, stay there for a day, then fly back for 2 days. So I'm going to see a lot of the airline food. So it's nice to see that they are coming to spring. So the temperature is September 21st, right? So it's almost the same as here. So the TA would cover those two classes. So do you have any questions about the stuff we covered last week, especially the networking aspects of it, the MAC layer and things like that? How's the projects groups coming along? So do we have a groups like do you? So who? Can you tell me like who your project partner is, or if you're working by a little bit about what you're thinking of, some high level stuff. I can start from
Okay. Looks like I'm going to be working with Pramita, and we're going to do some geography-based routing.
Okay. She was she's right there. Okay.
So.
As we're doing high level. Okay. Yeah, finalize the project partners first, right? I mean, that's the harder part. So something with geographic routing. Okay. And
I'm just going to work by myself and working on measuring energy-saving, based on turning on and off the CPS device.
I guess for myself, and maybe collecting some data of something that I can use for my project temperature.
What do you?
We're doing PAT, and we're just doing tracking using a bunch of different cameras and 2 computers.
Yeah.
I'm working with Ryan, and we're thinking about doing something like purely code-based with like scalability issues and like trying to get like auto patching.
Oh, okay. In what context? Like what?
Just trying to write software that can patch small, like just change the function of something as small as possible in like large quantities and see if we can
okay.
work for different.
More in like a regular general purpose machine kind of stuff. Okay, sounds good. Yeah. You guys are?
Yeah, we're with.
Okay. Do you guys know what?
No.
Okay. Yeah, you guys should start thinking about what you're working on and stuff. Especially at this stage, I think I mentioned to different people at different points, right? I'm not looking for the course. I'm not looking for something to be completed. I'm more interested in what you learned, not, the process of what you learned and what you kind of stuff, but not, the final learning point doesn't have to be new or exciting or whatever. It has to be exciting to you, right? So one of the things, to get there, you need to start getting all the infrastructure and stuff. So if it's software, you have to learn whatever has to be done. If it's a hardware, you have to get the resources and stuff. So I want you to start thinking about what you would like early on. So what I would really want is at the end to have something that you can talk about. So you have a presentation. I don't want you to say, we wanted to do 1, 2, 3, 4. We just did 1. We ran out of time, right? I don't expect necessarily for you to go all the way to all your 4 steps, but enough that you can give us a flavor that you learned something, right? Not like, like for example, if I take the patching stuff, right? We learned how to patch. We just read some manuals and figured out this is a way to do that, and that's how we did, right? And that's not a course project. That's more a report kind of thing, right? And if you have any questions or something, drop by, and especially in terms of getting hardware, resources. Like I said, I'll be gone next week, so I think the report is due the week after that, right? So, make sense? So we still continue from the textbook. How many of you read this chapter? Many of you who actually want to work in localization, yes, I
was thinking of myself, talking myself, sorry.
People who want to work in localization should read that chapter, right? It gives a very high-level kind of overview of some of the issues. So here we're talking, so now that we have all these networking issues solved from last class, so we know somehow how we can communicate with other nodes. And the next is to build some kind of infrastructure on top of it. And most of your projects, from what I can tell, kind of land in this zone. So you'll have to understand at least what's been done, right? Even though you may repeat what's been done, but you have to know that you're repeating what's been done, so you can kind of avoid some of the pitfalls, right? So the idea here is all these sensors have been deployed, and you want to build some sort of infrastructure where we can do nice things. And in the subsequent lectures, we look at what those are. You may query them or what have you. So you want to do something with the networking to build a higher level infrastructure, right? And part of that involves, so when you throw a sensor into a network, when you deploy a sensor into a network, it has to figure out who its neighbors are, because it probably can't, it does not know how to talk to anybody. So it has to figure out who its neighbors are so it can build the infrastructure, so it can kind of bootstrap itself, right? Before that, it will probably have to go through a phase of initializing itself, right, with whatever patches which may have come to it or what have you. So it initializes itself, checks all the sensors, recalibrates them. We don't mention those here because they tend to be more of the hardware kind of aspects. So once they're calibrated, now it has to talk to other nodes. And it talks to other nodes and sets up a sort of infrastructure. So you want this process to be scalable, right? So one way to discover and be part of the network is assume that every chair is a sensor, right? And I come into the room. I could start the process by telling everybody that I'm here, and when I leave, everybody learns kind of stuff, and that's not going to be scalable. So you want to somehow not propagate this information towards the whole network, because nodes come and go all the time. So you want this stuff to reach some nodes. So you want to be localized and still be able to reach a whole bunch of nodes. And once you have that, you need to set up the temporal and spatial framework, and that's a nicer way to say time and location. So you need to figure out where you are, because many of the systems would want to know what the location is, right? Either explicitly or implicitly, right? Most sensor setup would like to know where something was found. Given the large area of deployment, you want to know where things are. And temporal is important because otherwise you can't have any meaning for that. So if you say, I noticed, I measured some temperature, you need to figure out where the location is, and most importantly, what time it is, because time defines what kind of queries you can do with that. And so the example I gave was, if you're noticing a truck going by, right? And if it goes through a bunch of sensors, you have to know the sequence, right? You have to say this, the sensor 1 saw it, then sensor 2, then sensor 3, then sensor 4, then sensor 5. If you don't have this order, then you can't correlate that to figure out what's happening, right? So for some applications, you probably need the exact precise time. For some applications, you need the ordering. You need to know that this happened next, then next, and so on, right? The scenarios where you need the exact precise timing is if you're trying to figure out the speed, right? So if you want to see something moving this way, you can figure out how far apart they are, and based on how soon they detect that, you can figure out what's the speed of the particular event which is passing through, right? So depending on that, you have to figure out what the time is. And those are very hard problems, and as many of you who work in this field realize, the solutions for them are, I don't think it's still adequate, right? The problem is, many of these problems have been pseudo-solved in the networking distributed system sense by having lots of network packets going through, right? And you can't do that. So you want to avoid the number of messages you send to achieve these goals. And also you want to work with imprecise components, right? A good clock is more expensive, right? Whereas the ones on the sensors may not have a good clock. And a good clock should be in a temperature controlled setup, not lying around on the floor. So those things affect the things. So it's a harder challenge than distributed systems, traditional distributed systems. And you have much less resources to solve the same kind of problems. And how do we achieve that is what you're trying to do. And so the book chapter splits it into a number of different sections: topology control, clustering, time synchronization, localization, etc. Right? And for all of these, you assume that the network is set up and network is able to transmit something. Right? Before we proceed, one of the hardest part where the book does not, I don't think, do a good enough job is to understand the reality and what the mode of theoretical community would want, right? The notion here is how to send a packet and receive a packet, right? So if you want to do a distributed way of figuring out how much time something happens, you have to be able to quantify different processing steps, right? So suppose you have a node here, and suppose it has a clock. Right? Your goal is to somehow get these two clocks to be synchronized or what have you, or try to figure out what's happening with the clock, right? So think of this as wristwatches, and suppose this one is saying 10:15 and this is saying 10:16, right? You want to do something, maybe synchronize it to 10:15 or 10:16 or what have you. The way you do that is obviously you cannot watch from here what the clock is, so you have to send a message, right? So you create a message, let's say with the time 10:15 in it, right? And you send it across, and then it goes over the wireless, and then it's received, and it goes up, right? And it comes here, and we'll see in the later on chapter what you do with it. You do some kind of stuff to figure out what, you can do nice stuff with it, right? For in this system, right, there's the operating system component here, there's the operating system component here, right? And then there's the network interface, which may or may not be separate, right? On a simple machine, it may not be a separate component. Remember, one of the things we said was you finish the processing all the way till it goes on the wire and then move forward. On a laptop kind of things, these may be a separate kind of thing, right? And then it goes through something here, right, which we don't know what it is. So you have to model what the environment should be, right? You have to model so that you kind of can make sense of. So all these add delays to it, right? So let's say this is D, and these components add delay, these components add delay, and so on and so forth, right? So if you can figure out all these, what all these delays are, and you can say, if you receive this 10:15 message here from this node, right, plus this delay, right, would sort of tell you what time this node is. So then this machine can compare this this with this, right? Can compare with whatever it's seeing in the clock to do something, right? So can you think of some of the reasons why this is very hard, right? The hardest part is, assume the clock, it's existing right now. The hardest part is to figure out exactly what this D should be, right? Yeah.
Different manufacturing or temperature even can determine how fast it propagates through the hardware. So like the delay can change on a regular basis.
Delay on which part?
Just through the circuit itself.
Yeah. So you mean like this part, right? There's a temperature component which figures out how long the signal takes to go on the wire, right? So that's one of the components, right? It's the temperature of wire. What other factors would affect? We talked about some of these in the, I think, intro lectures and stuff, right? Let's look in here. Can you exactly predict how long this delay would be? Right? It's very hard to predict what the delay is, right? Because depending on what the technology is, there may be a number of reasons. One is the temperature, humidity, and all those things. The other is you may have multipath and other stuff depending on the technology, right? Multipath basically says that the signal may go this way, or there may be something here. So signal may actually go this way, get bounced around, and comes back here, right? So this signal travel longer to get to this part. So your your message may go directly this way or may have come through being bounced around from somewhere. So depending on how you're doing stuff, it's kind of hard to figure out what's happening at this point, right? And we still don't have a good sense of handle of what these things are. And a lot of people are trying to model real world to see what these values should be. So what about here? Right? The hint is an operating system, right? Some of you took operating system with me. Some of you took grad operating systems, right? So what would be the problem within this component, on that component? Do you remember how you would send a packet? What are the events which happen from a packet or something from application all the way out? We may not have directly said that in the undergrad operating system, right? Yeah.
You have to make some sort of system call.
Yeah. So you make some sort of system call, right? I don't think we went through that explicitly in operating system, what happens, right? Think of this, like for people who took operating system, think of how it happens when you're trying to write something to the disk, right? You have a data that has to be that goes through a disk, and assume this is a disk, right? Do you remember what are the things which happen between these two? Yeah, you have a system call. What happens when you do a system call?
Wait for the system to tell you that.
Yes, a soft interrupt, right? System call is a soft interrupt. So when you make this call, there's a soft interrupt to a CPU, and it puts you in some queue. And when at some point, right, hopefully sooner, it takes it off the queue, it reacts to it, right? And it goes through some processing inside, right? And if you take networking class, you'll know what those processing are. But let's assume that it's taking some little bit of time doing the processing, right? Then you have to send it to the disk or some IO device like network card or what have you, right? And depending on the operating system, depending on the system, you rarely directly manipulate the network, right? Sometimes you buffer them or what have you, right? So they add delays. I mean, there's a delay of even on the real modes and stuff, right? When you want to send something, unless the device is not doing anything else, it has to prioritize on what it's doing, right? So in a small mode that they're talking about, if it's doing something else, it'll have to wait, right? So that wait time is not bounded, right? So it may take some amount of time. This wait time is not bounded, and the same way, going back, somebody gets it, you get an interrupt, you actually get a hardware interrupt, you process the interrupt, put it on the right process queue, and then it goes to the application or what have you, right? So they all add delays, right? So essentially, when you say 10:15 and it comes to 10 plus D, you don't know precisely what the D is, right? If you don't know what the D is, then you can't really say much about what's happening between these two machines because those things are unknown, right? So consider another case. Consider a theoretical case where this delay is 0, right? And this delay is 0, right? This is theoretical because obviously a real system cannot do that because it has to deal with other issues. And this delay is a fixed D, right? It's a constant, right? In that scenario, can you solve this problem? Can you solve this problem where they somehow figure out what the, they come to something with the time, right? Can you figure out this D on the fly? You don't know what D is, but you know that D is a constant, right? Yeah.
Send messages back and forth to try to average it.
Yeah, so you send a message and then you see what the, so essentially you send this stuff and then it gets a 10, 15 plus D, right? And you send something back saying either that message or different messages, right? In fact, that's what your ping does, right? Ping assumes that this is 0, and it keeps sending packets over and over again and gets the response back. So you send a packet, it goes all the way here, it immediately gets bounced back, right? All this node has to do is bounce it back. And you sent it at 10:15 and you got it at 10:15 plus 2D, right? So you half it to know what the D is, right? So those are, if it's theoretically simple system, those theoretically simple solutions work. But obviously the world is not so simple, so you have more complications. So we'll go through different ways of getting stuff done, right? Obviously this is easy, and obviously this doesn't work, right? Or it works to some extent, right? Depends on how precise you want the clocks to be synchronized, right? In general, how precise do you think you will want the clocks to be synchronized? Thinking of some sensor system that you worked on or thought about. If you have two sensors, to make life easier, I'm going to figure out how fast some object is going from this end of the room to that end of the room. And you have one sensor here, one sensor there, right? And assume the sensor can only detect a close range, right? How precise should the time be of? Not in exact numbers, but what is the bounding condition?
How fast the objects are moving, or how fast you think they might be moving?
Yeah, you want the resolution to be bigger than what the object speed is, right? Because it adds an error condition, right? So depending on how close you can get the clock, you say plus, the time is plus or minus 10 milliseconds, right? So for example, in this case, if you say the time between these two clocks are plus or minus 10 seconds, right? That means you need to have basically a snail moving across, right? Because it probably takes it more than 10 seconds, so you can say could be done maybe plus or minus 10 seconds. If it's me walking across, I would probably cross across a few milliseconds. So you can't know whether I went from here to there or what have you. So the application drives some of these requirements, right? And some of the more interesting cases require highly precise synchronization. If you're talking about a vehicle moving at 80, 90 miles an hour or something, then things move very fast. So you need to have it fairly synchronized, right? So that's sort of the background of what has to happen. One of the problems with the book is it's fairly theoretical, right? In some of the things they kind of wish that some of these things away, but from a practical perspective, some of these things are very hard. So when you try these things, so people who are doing this as a research, you realize how hard these are to keep these things synchronized, right? So for the grad students who are working on projects, right? How do you deal with these synchronization issues, especially like the team track? But I guess you guys have a GPS, so.
Yeah.
Do you use the GPS clock?
No, I haven't done anything.
Okay. Because one of the nice things about GPS is it gives you a clock for free, right? It gives you the synchronized clock, very precise synchronized clock. So if you can run GPS, then you don't have to worry about a whole bunch of these stuff, right? GPS itself is more energy consuming, right? So let's go to the different aspects of this problem, right? And again, these are all fundamental techniques, and obviously the state of the art has moved a little bit further, right? Not so much because the field itself is, less than like half a decade or less than a decade old, so it's not that mature yet, right? So the first problem is you want to figure out who your neighbors are, and the problem becomes more interesting because your neighbors need not be static. Even though the nodes may not move, the neighbors are not static because they may die off because their battery runs out, or they may reduce the transmission range, so they are no longer your neighbors, right? And one of the assumptions that they make about how the range and all works is apparently not true. Like talking to some of the EE faculty, right? So the assumptions that they make is if you are a node and if you want to transmit to somewhere here, right? And if you want to transmit to somewhere here, right? That you can do the transmission power control to say, I want to transmit from here to here, or I want to transmit from here to here. There's an equation which figures out how much energy you want, right? But basically, you can plug that equation and say, to go from here to here, you need so much transmission power, right? The power on the signal has to be so and so. And then they take it to the next step and say, since the power to transmit is, let's say this is P1 and this is P2, right? So they say, so since this is P1 and this is P2, the amount of energy taken from the battery is proportional for here, is proportional to P1, proportional to P2, right? That's the assumption that this book makes, and a lot of people seem to make. And I don't have much of a hardware background, but some of the hardware folks tell me that that's necessarily not true, right? All it says is that the transmission system takes this much power, but the power for the entire system it's constant, right? So essentially, you have let's say this is the transmitter, and you have a resistor. So in the first case, you do P1 here, and then here you do P minus P1. And the second case, you do P2, P minus P2, sort of, right? So essentially, when you reduce the transmission power, you heat up the device more. You increase the transmission power, you don't heat up the power more, right? So it does not work for saving energy. I mean, unless your goal is to save energy. It has other benefits. You avoid spatial reuse, right? Which means that if another node is here, you could be talking to here without interference, too much interference, right? But this book makes the assumption that you can do the power in some nice fashion, right? So if you go with that model, which is a fairly simplistic model, right? So there are reasons why the nodes would reduce the power. So they want to reduce the power to conserve energy. So what you thought as a neighbor may no longer be a neighbor because it's reduced its power. So you have to keep track of those, right? And the challenge here is you can't keep track of that by being actively looking for the stuff. So you have to still sleep a lot, right? Still stay idle and still know what your neighbors are. And that's the biggest challenge, right? So they talk about a number of different ways to solve the problem. And one of the things you realize in any of the computing sciences, which is one thing I know, is the first set of papers phrase them in a very theoretical context, right? In which case, you come up with some nice algorithms and either prove the NP complete or, not complete, right? I mean, if you have algorithms background, I'm sure the grad students have. You guys have taken the algorithms yet? I guess you'll take it next year, right?
We're taking algorithms right now.
Right now, okay.
CPEGs don't have to take it.
Oh, okay. So, yeah, okay.
Yeah, computer science has to take it. We're taking it right now.
Okay. So do you like the course? I don't want to put you in the hard spot, right? But I personally don't like the course. But anyway, so luckily I don't have to take it again now. But anyway, so one of the things I hate about the class is, you come up with a way to beautifully do something and then show that it's NP complete, right? But essentially, so you can make the problem into simpler cases that can be analyzed, right? Because I don't think they don't try the harder cases. It's just that harder cases are so hard that you can't analyze it theoretically, right? Some of the let's look at the simple setup, which you can realize it's not really feasible, right? The first problem you're trying to solve is a made-up problem, right? Where you have a bunch of nodes, they are somehow deployed somehow, right? You're trying to figure out what power range that, in this case, all the nodes have to transmit at the same power. You have to figure out the minimum power that any node has to transmit such that all the nodes are connected, right? So it may mean that, the connectivity may have to be something like this. I'm just drawing it like this, right? But essentially, you're trying to figure out what's the minimum power necessary for such that all the nodes can be connected to each other, right? The other problem, what's the maximum power, is trivial, right? Maximum power is you find the two extremities, and that's the power you want. So in this case, it may happen that this and this is the furthest out. So you have to worry about that, right? The other way is to find out what's the minimum power needed such that the whole network is still connected, with the constraint that all the power of the maximum would be used by every other node, right? So for example, in this case, let's have a node here, just to emphasize the stuff, right? And let's have a node here, right? So in this setup, it's highly likely that the answer would be this, right? Because this is the furthest from the system. So when the system operates, all the nodes would use this much power, this much transmission range. So this node would transmit, so it can come up fairly till here, sort of thing, right? And that's called the critical transmitting range problem, right? You want to find the minimum common transmission power for all the nodes. And the solution for that is the longest edge of the minimum spanning tree, the Euclidean spanning tree, right? How many of you know that algorithm? I'm guessing the algorithms, if you're taking algorithms, you probably would know that, right? For people who took networking, this problem you should remember this. You should know that, right? How many of you heard it from the networking class? Yeah.
I don't remember exactly.
I'm sorry?
Exchange messages and try to find. I remember the algorithm exactly.
But what were you trying to solve?
Routing issues.
Yeah, you actually use it to solve in the bridging issue. Like, it doesn't scale, so you use it in the bridging sense, right? So if you're talking about Ethernet, right, that's what they try to do, right? Ethernet, if you, for people who took networking class, Ethernet, nobody does the Ethernet, the CSMA CD Ethernet anymore. So you're trying to do switch networks, right? So you have a switch and a whole bunch of machines, right? Ideally, you should only have like this and something like this, where there are no routing loops through the stuff, right? But for practical reasons, that does not work. So you typically have multiple paths to get through, right? And one of the bridging problems you need to solve is you need to cut off one of these paths, because if you don't, then the broadcast packets will keep looping over and over again, right? So you want to run the minimum spanning tree algorithm, which is essentially this one, right? To figure out which nodes, which links to prune, which links to keep around, right? Does that ring a bell for people who took network class, right? Do you remember how the algorithm ran?
Isn't greedy somehow?
I'm sorry?
The smallest width first?
Yeah, but like steps, like how does it?
We start from the source node and then.
You flood.
Yeah.
You flood these casts through multiple things to figure out what's happening, right? So the key to remember is those algorithms need lots of communication, right? They have to figure out what's the shortest path by, this node knows this bridge knows what this length is. It's a global algorithm. It's not a local algorithm, right? So you're not trying to figure out what's the shortest path here. You're trying to build the minimum spanning tree, right? So one node has to build the minimum spanning tree, right? If you go back and look at the Ethernet case, so it has to collect all the data. It figures out what the stuff is, and it has to get rid of paths, right? It's not a localized algorithm. So here, when you want to do a global algorithm, some information has to go to some entity, right? And those don't scale, right? So you can't run those algorithms here, even though you would like to. Theoretically, that's the solution, right? Theoretically, you build this, global minimum spanning tree, right? And you can figure out what's the longest length on that, and that's the answer, right? That would mean that somebody has to take responsibility for the whole network. So it's not practical to do that. You can't have multiple rounds of communication, right? One, it's too resource intensive, and two, it doesn't matter anyway because the nodes may go away, right? So I may find the local, I may go through this expensive process, and then the node goes away, and we are back to square one, right? In the case of the Ethernet networks, routers rarely change, right? So you don't have to run this protocol every hour or so, every minute or so, right? for people who take a network administration, right, or network Kurt Phelan's class, right, you may have learned about what happens when a bridge begins to misbehave, go on and off, right? Have you, like, has anyone taken a network administration kinds of class? Yeah.
Yes, it starts broadcasting messages. Papers that it's up. Yeah. So it's flood. It's going to start flooding. It comes back up.
Yeah, but what happens? Actually, in this case, if it tends to go through that, your route will keep failing, right? Because they may kind of converge to a state saying, let's use this route, and then something else comes back, and then they decide, let's use this route, or let's use this route or something, and things begin to oscillate, and you bring the whole network down. Frequently, we do bring the network down, sometimes it fits and stuff, right? Somebody plugs some cable here, and somebody starts screaming, because they don't assume that routers and bridges are changing every few seconds, right? But which is the case here. So the algorithm is nice. It's a theoretical foundation. You can find out what the bounds are. They're not practical. The even more interesting algorithm is the probabilistic solutions, like the geometric random graphs. I'm not going to go through how that works, right? You can read it on the textbook, right? It seems even more removed from reality, right? It gives you a bound of what's the transmission power and stuff in a probabilistic fashion. But it's even more harder because all these things require so much communication between the different nodes that it's not practical, right? And besides, the simple setup itself seems kind of strange, right? Because the example I had, if there's a node here and there's a node here, there's no reason why every node has to transmit at that same power, right? Doesn't seem to achieve so much. So more realistic scenario is to allow different nodes to vary the transmission range, right? For whatever reason. I mean, you can assume it's for saving energy, or you can assume to reduce the stuff. But the reason always holds, which is if you have lots of nodes here, right? It probably makes sense, and some of the nodes over that side. It probably makes sense for these nodes to keep the transmission power low so they can communicate with each other. So if each of them was transmitting at this range, right, that means only one can be transmitting at any one time, assuming you're using the same channel, right? But if each one of them can only, like if this one transmitted at this range, then that means potentially somebody else can transmit over here. So when there's lots of these sensors, you want to keep the communications fairly tight. But if you have to talk to somebody further out, then you may have to increase the power, right? So there are reasons why these are necessary, at least from the network perspective, right? And as you can imagine, with most algorithms, that's of course NP complete. NP complete for people who haven't taken algorithms course, it's really hard, which is another way of saying it's impossible, right? So don't try that, right? So there are several of these techniques which are resource intensive, and it's still ongoing research trying to figure out how do you generate these topologies, how do you make them work, and there are more protocols that the book kind of touches upon, right? But in general, trying to figure out what the topology should be, it's a very hard problem, right? And people are still. I think that one of the awful things with the networks, the sensor systems, is how little work has been done in the sensor setup, right? You'll be surprised to notice that even the most rudimentary thing that you expect to have been done is only now somebody's doing in real setup, right? And people who have done that, I think you've done some of those, and many of you have done some of these things. Realize that things don't actually work anywhere close to what the model should say, right? And that's one of the most interesting times to be, right? Because the way I said it, the first, the more theoretically oriented people would come through, right? And they develop a lot of theorems and stuff. And then the more simulation-oriented folks would come in and simulate and say this will work. And then the systems people come in and say, none of those work, and we'll solve it in a different way kind of thing. So I think we are in that kind of phase. So that's the problem of dealing with this. So when I mentioned that there's a whole bunch of these nodes, right? That brings up an issue of if there's all these nodes like so close together, several things happen. One is they may all be seeing the same phenomenon. So if you're looking at temperature, right, it's highly likely that all of these probably have the same temperature than something over here, right? And so on and so forth, depending on what the sensor is, right? So it's highly likely these things are all going to be the same reading, right? Yeah, question? Oh, I think, okay. So they have the same reading, right? But it's good because if one of them goes away, you still have some values from here, right? So what you would like to do with this scenario is have some sort of a representative for this area, right? Somehow we call it clustering. You cluster them, have some sort of a cluster head or what have you, and create a hierarchy where this cluster head does something local processing, right? So it does not need the whole thing. So it can figure out if it's a temperature, it may sample a few nodes. We don't care. For the rest of the system, this cluster head is what talks to the rest of the system, right? So it avoids the notion of keeping all these nodes online because they're all clustered. The other nice thing is if this node asks for the temperature, right? You don't want all of them to be transmitting so many messages here, right? You know for a fact the temperature didn't change that much, but even if you didn't think it changed that much, you don't want all these long distance transmissions, right? So you do the airline hub model kind of thing. So you kind of collect everything into one cluster head, collects everything, and that node asks the cluster head. It can do whatever to aggregate the data. So it may sample, it can do whatever, but then you send one long distance message, right? So that's the notion of cluster. Essentially, you're creating hierarchy, right? So instead of having any node talk to any node, you create these clusters and somebody asks them, right? Like a sort of like a military kind of sense, right? So the question is, who should be the cluster head, right? So who do you think should be the cluster head? Yeah.
One that's in the geographic center.
Yeah. So geographic center is. Yeah. The criteria. You have a guess?
I don't know. If the sensors are different, probably should be one that would be able to handle all the extra transmissions and stuff.
Yeah, resource rich. Right? You want the one which is most resource rich. Because you want something which is good to be a cluster head, right? And there are many other ways you can think of, right? And of course, that means there's a paper talking about just that, right? So one of the things you may want is, you may want a cluster head which is closest to the rest of the network or what have you. Frequently, you may not have one resource-rich node, right? Or it may not stay resource-rich forever. So you may want to rotate these things. So you go through different protocols which figure out who the cluster's head is, right? How would you do that without telling you anything about how you may do that? How would you figure out? Let's assume this is not happening. Let's assume you're not going with this, right? Any one of them is good. How would you select who who the cluster head should be? Any solution you think of is probably accurate. Just randomly assume that I picked this one, right? This is the cluster head now. And how would you pick from here to something else? What are the steps you need to do?
find one that can also take on the duties of the...
Yeah, so you need to find somebody who's good, right? So how do you find that?
You just ask them, I guess you just talk to the members or send a bunch of packets, figure out if they have that bandwidth or whatever.
Yeah, so you need to ask somebody, right? So the first point is who's you, right? The you could be this, right? But in the general sensor setup, there's no you, right? It's a complete democracy, right? There's no head per se, right? So they all have to figure out who's a good one, right? So they all have to do a distributed algorithm. You don't want somebody to ask each one of you, are you capable of doing some stuff, right? So somehow somebody figures out that there is no cluster head, right? Let's assume that this went away, right? So every one of you, so if I leave the room, right, and you guys are here, you want to find somebody who can come and give a lecture, right? So somehow you have to figure out, right? So in this case, you'll probably sit there for a while and you notice the room is very quiet, right? Let's assume that you don't have eyes, right? You notice the class is very quiet. And then you say, oh, something is wrong. Maybe the instructor left. We need to find somebody else, right? So you speak up and say, is there anybody who can be a cluster head, right? Unfortunately, all of you would ask the same thing, right? So eventually you guys talk amongst themselves to figure out who the cluster head should be, right? So even the simple task need not be simple, right? I mean, hopefully it's all contained, but you all have to talk to each other and figure out who should be the cluster head, right? Do you think it's difficult among human beings? Like for example, you all want to figure out some time to have a meeting after this class to figure out something, right? Figure out how to do the project, right? Have you ever tried to schedule all of 10, 20 people to come up with a time? You guys must have had the experience, right? I call it NP hard, right? Because it's always kind of hard because you have to go through endless iterations where he says he can make it 4, and then you kind of figure out it's 4, and then somebody says no, I want to change it, and he goes back and stuff. So that's one step. So you go through all the stuff and you figure out that this is now the designated cluster head, right? You also have to forget the fact that in a real system, in a different kind of system, there's no motivation for this person to be a cluster head. I mean, they're not probably gaining much, right? In a sensor setup, you assume that everybody's doing this for the goodness of the whole system. But in real life, that may not happen, right? So if I walk out of the room, how many of you would want to come and take the class, right? I hope it's all of you just wants to run up and take over the class. But it just may be the case that people don't want to come up here. So there's no motivation for you to do it because you're going to spend all the battery life for others, right? So you have to sort of find the sucker who wants to monitor to this one. So you found this one, and so once you find it, we all have to agree, right? Which means that everybody has to get the message back that this is the cluster head, right? Because then they expect some sort of a thing. Are we done? Yeah.
Kind of monitor to make sure that one doesn't disappear.
Yeah. So yeah, you have to elect a cluster head, then monitor the cluster head. And what's the step 2? Actually, they have so many errors here, but I said we want to avoid this by sending it to the cluster head, right? Yeah.
Notify polling nodes or other nodes.
Yeah, so you need to talk to all these people to tell them where the cluster is, right? If otherwise, so the whole reason is one of the reasons is you want to make sure that this one talks to the cluster, so you don't want it to be addressing somebody else, right? So you have to propagate these things. So it's a fairly involved process, right? And you have to do that. I mean, you have to do that frequently, right? So you would like to choose cluster heads who are resource rich and at least who has GPS and good energy and stuff. And having a GPS enabled cluster head means that you can get time from that. So you can synchronize your time to that clock rather than completely out of the blue. And energy, you wish, you hope the energy would be there, because otherwise you have to go through this process again and again. So you want to avoid this election process. And the way to avoid that is to keep the cluster head on for a while, right? And you build hierarchies where the cluster, group of clusters form a gateway, choose a gateway, right? So eventually you say this cluster talks to another cluster kind of thing, and then eventually goes to a gateway, and from there it goes outside the system. So the human or somebody is monitoring the sensor at that point. So gateway is how. So if you want something, you don't talk to all the sensors. You talk to the gateway, and the gateway talks to different cluster heads and propagates and get the results back, right? And within the cluster, since we are all cluster head, the cluster head can manage lots of resources. So for example, it can manage the network schedule on when people should go. Remember, one of the schemes we talked about was a TDMA-based scheme, where somebody says who should talk when. And since it's a cluster head, it can arbitrate these things. So you actually get better MAC protocols here, because this one can control all the other nodes, right? And they form a gateway of sorts. So that's one of the problems that we have to solve. How do you organize these things? And so through these mechanisms, you can create the overlay, of reaching nodes, and we had achieved scalability by having these little clusters, and then form a cluster of clusters to be able to reach the whole network, right? So you partition the big problem into small problems. So I think one of the problems you mentioned at the very beginning was how do you scale to a large number of systems, right? So hopefully we know how to process something here. And if you want to know something in this system, have you noticed a car? What's the temperature? What have you? You don't ask individual nodes. You just ask the cluster head, and somehow it's solved, right? And you create more hierarchies like this, right? So next problem, does that make sense? Again, we're still talking very general, very fundamental, basic kind of stuff. We'll see more papers which go into more detail about every aspect of it later on, right? The next aspect is time synchronization, right? You want all these things to be synchronized exactly, like I mentioned at the beginning of the class, to be on the same time, because otherwise the observations make no sense, right? You need to know when something happened before or after. It's also needed for ranging and localization things. If you want to find some distance, you want to find out how much time it took for something to go and come back. And you also want it for these schedules, right? So if you're using TDMA kind of scheme, where you say who goes next in terms of transmission, right? I can say I'm going to go to sleep for 10 milliseconds, and then I'm going to wake up for data. If you have data, send me every 10 milliseconds, right? If our clocks are not synchronized, then you'll be transmitting when I'm sleeping. I'll be waiting when you are sleeping, and so on, right? So in the wired world, we use NTP. How many of you have used NTP protocols? All of you must have used it, because most of your machines these days, when you set up the machine, will ask you for a time server, right? It'll say time.apple.com or time.microsoft.com or time.nd.edu or something, right? These are good clocks. They are synchronized on using atomic clocks. They're very stable, and you constantly send messages back and forth to a couple of these things to keep your clock in synchrony, right? So what you're trying to do is you have machine 1, you have machine 2, right? And assume the clock is ticking like this, right? Ignore my quality of drawing. Let's assume this is 1 second, right? This is 2 seconds, this is 3 seconds. So, like, tick, every second you get a tick or something, right? And you have another clock here, right? And these ticks are created by hardware oscillators. All the machines have an oscillator, and so you have something like the oscillator goes at, let's say, this many clicks per second. High-speed oscillator essentially. But essentially, every so often it creates an interrupt also, and you create these clicks, right? What you really want is these things to be synchronized. and these things to be synchronized, right? That involves two different problems. One is to make sure that this and this are at the same time, right? Which is both the clocks are at the same time. And the other problem is you want to make sure that this is not happening, right? Where what this clock thinks as 0 is really 1 here. They're phase shifted, right? Where they both appear to be synchronized because they're both going exactly at the same period, but one of them is further into the future than the other one, right? And I think that's in the next slide. So this is the notion of a phase. So you want to keep these phases the same. You want the clocks to be the same, right? You want the clocks to be synchronized all the time. And you want the intervals between them to be the same, right? So that means I have to synchronize this and this now, right? So that means that my clock and your clock are at the same tick rate now. It has to be the same time, right? So you cannot have the phase shift. And if I come back in 5 minutes, we are still synchronized, right? If this happens to be 0.99999 of this interval, right? Eventually this will spread apart, right? So the problem is I need to synchronize it, I need to keep the phase shift same, and I need to maintain it, right? In the case of NTP and all those things, right, they can constantly keep making sure that it's always synchronized. They can constantly keep checking this. You constantly keep sending packets every so often and stuff. Whereas in the sensor case, you don't want to do that, right? And to make life more interesting, all these depend on this hardware clock, right? There's some hardware clock which is dividing to create this stuff, right? Which means that let's say every 30,000 hertz or something, it divides it to create this one clock, right? If the oscillator was cheap, right, and it only did, right, then the division would mean that the time is off in a certain way, right? So the oscillator could be cheap, or the oscillator could be in a room where it's hot or cold, right? So if you have hardware background, right? All these things, if you change the ambient temperature, computers don't really like to operate that precisely, right? And exactly that's the way we expect the sensors to work, right? Sensors, you don't typically have a high quality clock. You don't expect, especially keep the good temperature. So depending on what the temperature is, these things are wildly changing. So when it cools down, things may change a little bit. When it heats up, things may change a little bit, right? You may have noticed this. I mean, how many of you trust your computer clock to keep good time, right? You do? Without NTP. Without NTP kind of thing. No, you have, I mean, oh, yeah. No, I can't correct it. I'm saying remove all kind of external, yeah. Take the network card out, right? No network, leave your computer, right? How many of you trust the clock? How many of you watched your clock go? Yeah.
It changes, it gets off, like after a couple hours or so, you see it's, up to like a whole couple minutes off.
Yeah. Is that what you're... They're awful. I mean, yeah, they're visibly off, right? Like within a day, it goes off like 15 minutes or something like that, right? So you appreciate how difficult the problem here is, right? You have a laptop or a computer which has a lot more better components than what you see on these systems, right? And I'm guessing most of us don't leave the laptop in the snow or in the heat or whatever. I mean, it's in a fairly decent temperature setting, right? And the temperature goes off by, I mean, the time goes off by a lot. So on a thing which is deployed and staying there for days and months, right? If it drifts off by an hour, right, in a week, right, then it's disaster, right? So this sensor is going to say, I noticed a car at 11:01, and this is going to say, I noticed a car at 12:01, and this is going to say, I noticed a car at 10:01, and this is going to say, I noticed it at like 11:30, right? Then you have no idea what really happened because you have no idea what happened. So you want to keep these things synchronized. And so frequently you find that you cannot solve the global problem, right? You cannot solve the problem of a global time, right? You cannot ask these sensors, did this happen at 11:30 from my clock? Which means that my clock has to be synchronized with the sensor stuff, and that's much harder. So what you settle for is if it's locally synchronized, right? So I have no idea what your clock is. I just want to know what time you saw within the time that you all agree, right? That's a local synchronization. So I cannot ask you absolutely what the time is, but I can ask you what time is it within your context, right? And another way of reducing that is to figure out what's the order, right? You don't really care what's the difference. So it may happen that from here to here, it took 1 hour. From here to here, it's 1 second. You don't care about that. You want to know which one came before what's the other one, right? So those are ways where you can still make it manageable. You're not getting as accurate information as what you really may want, but the real information is so much harder to achieve, right? So that's the thing I mentioned. All these things have a hardware oscillator, and the accuracy of the oscillator defines how good a clock it is, right? And that's why the time clocks use a cesium atomic clock, which is very stable, and your laptops and computers don't have that precise clocks because it adds cost and what have you, right? So the skew is the notion that these things move around, and the phase is the notion that even though they're synchronized, they may be synchronized to a different tick, right? So whatever this measures, if this says I measured it at time 1, and this says I measured at time 0, those are synchronized, not necessarily the previous ones, right? So there are a number of works that the book talks about how to keep these things synchronized. The simple one is to use a message to figure out so the mechanisms involve basically sending some message. So each node sends some message with some kind of a content, right? And we'll see different algorithms. And the receiving node has to do something, send it back. And based on the time between what was sent, what was received, we can make different judgments, right? And like I mentioned before in the OS case, this assumes that you know precisely what's the operating system delay on the sender, on the receiver, on the wire. We can control the receiver end by basically putting the timestamp on the network card. Basically, the first time it comes to the machine, you can timestamp it. It's very hard to control on the sending side. It's impossible to control on the medium because that's the environment you're operating in, right? So you have the three components we talked about. This is the time to send through the machine, the time on the wire, time on the receiving side, and each one of them adds some delays, and we may or may not have control over them, right? So the first problem that they talk about is to try to figure out the clock phase difference, right? Which is trying to figure out there's a clock here, there's a clock here. We want to figure out right. So suppose these are two clocks like this. You're trying to figure out how much phase they're off, right? They're still ticking at the same time, right? So the way you do that is you have a node, right? This node is operating at time t1, right? This node sends a message here with the message with the time t1, the local time, into the message and sends it across, right? So when it receives here, the time it receives is t2, right? And t2 essentially is t1 plus d, the delay that we don't know what it is, right? And plus the phase difference, right? We don't know what that is either, right? It could be plus or minus. Let's assume plus for the sake of